Welcome to the fourth video of the 23rd chapter on SD card usage. In the previous video, we found out that we need to use a file system on the SD card in order to easily access the data saved by the microcontroller on our computer.
Since FAT32 is the most commonly supported file system on all systems, we will use it in our embedded system. Of course, we don't need to pull out the hundreds of pages of FAT32 specifications and write our software based on them, nor do we even need to understand exactly how FAT works.
We'll use the FATFS library, which takes the low-level operations off our shoulders, allowing us to read from and write to the SD card using functions that are similar to the standard C file operations. Fortunately for us, STM32Cube IDE comes with the FATFS library built in, so we'll be able to use it with only a few clicks.
Now let's set ourselves a simple goal to get a taste of using it. Let's write a piece of software that has the following features. It creates a file called text.txt on the SD card and inserts numbers from 0 to 255 as text, each followed by a new line character \n. Then, it creates a file on the SD card called binary.bin and inserts the numbers 0 to 255, but this time represented as 8 bits in binary. And finally, reads back the created files and checks their contents. If the contents of text.txt are not correct, LED 1 will blink. If the contents of text.txt are correct, then LED 1 lights up. If the contents of binary.bin are incorrect, then LED 2 blinks. And if the contents of the binary.bin are correct, then LED 2 lights up. In case of any other error, the run execution stops and LED 4 will blink.
First, import the included project Lecture 23 FATFS into the STM32Cube IDE development environment. Open the IOC file and see exactly what settings are in it.
You will find that the configuration at the peripheral level is almost identical to the Lecture 23 block project, with only a few differences at the SDIO peripheral. In order to make the FATFS library work fast, we increase the communication speed of the SD card to 12 MHz from 400 kHz used before. To do this, the division is set to 48 MHz divided by 12 MHz minus 2, meaning we set it to 2. The CubeMX source code generation function only supports DMA-based FATFS data transfer, so we need to enable that too.
The DMA, which is the abbreviation for Direct Memory Access, is a peripheral that can transfer data between registers on other peripherals and RAM without the processor.
To use DMA, interrupts must also be enabled. The priority of these interrupts cannot be higher than 5 due to the nature of FreeRTOS. This can be set in the System Core NVIC submenu. Under the Middleware tab, there is a checkbox in front of the FATFS line to select whether you want to use the FATFS directory in your software. The default settings are used, only the SD card insertion detection had to be changed in the Platform Settings tab so that the SD NDS GPIO will be used for this purpose.
To be on the safe side, let's regenerate the source code. A big advantage of CubeMX is that it adds the FATFS library and other libraries to your project in an automated way, usually ready to use after a few clicks.
As in the previous project, a framework software is already pre-built. Basically, we only have to work in fatfstest.c and fatfstest.h files. The parts to be implemented are marked with to-do comments. The fatfstest task has already been created in the source files, and it starts automatically when FreeRTOS starts.
It can be seen that there are 5 functions called in the task related to the file system management. The aim is to implement them. In the next video, we will go through each of these functions and what additional FATFS functions you need to call within them to achieve the given functionality. See you there.
Bye.
Bye.